Just letting you know.
Yeah, because when I'm being recorded, I'm very careful not to say anything that I'll regret. Yes.
Good. Oh, right on time. It's really good.
Oh, where's my notes upstairs? I just have to go from memory.
You want your notes?
Do I have 30 seconds?
Yeah.
Yeah.
Do we have any visitors today? I think it'll be better with his notes,
I have
right?
a visitor, which is Emily Jo Griffith, who's sitting here. She is from Colorado, postdoc working on nucleosynthesis in stars.
Excellent. Is that part of the genome there, or is that a different?
No.
No.
Yeah.
All right. Do we have other visitors?
Kevin.
That's pretty Thursday.
Kevin.
Hi, I'm Kevin Kelly. I'm from Texas A&M, visiting for today through Wednesday.
Cool.
Have seminars.
Have seminars. Other visitors?
Yeah.
Yeah.
Wong Yu, frequent visitor, visiting from Florida.
Ah, excellent. These are all me?
No, just today.
Where is the group?
David is getting his notes. So. But you also have had trouble with your arm, correct?
That's why.
Yeah, yes.
like
So you're saying that in sympathy. Yeah. But you had your right hand.
Oh, it's his left.
It's left.
He was wearing a sling.
Take it or? Take it or affect it or is it just
In his case, I don't know.
Anyway, cool. Talk amongst yourselves.
David, you look good.
Thanks. At least this is my bad hand.
All right. I'm glad we got that whole thing recorded. And now David has come, and he will tell us about new dark matter constraints from old astronomical tools.
Something like that.
Something
yeah.
like that.
Good. So I'm going to talk about, first of all, I'm going to give you some high-level comments, about why I'm doing what I'm doing. Then I'm going to tell you about, I'm going to remind you about things about dynamics that you are supposed to know. So I'm going to remind you some things about dynamics. And that's a little bit ironic coming from me because I'm the person who moved dynamics from a required course to an optional course in the undergraduate curriculum over the objection of several people in this room. And then I'm going to talk about stellar abundances, meaning what stars are made of. And then I'm going to talk to you about the Milky Way and what are the basic properties of the Milky Way that we know and that we hope to know. And then I'm going to tell you the real story. Because of this, it's quite likely that I will do the story injustice, but that's fine because the point of Brown Bag is learning. So we'll try to learn along the way, and you'll get a sense of what the real story is at the end. Okay, good. So in my potted history of the world, Halley, which was maybe pronounced Holly, figured out that the force law in the solar system is proportional to 1 over r squared. Actually, better to say the acceleration law in the solar system is proportional to 1 over r squared. How did that happen? People credit this to Newton, by the way, but Newton was famous for taking credit for other people's stuff, which is one of the reasons I don't like naming things after people. But anyway, this is a potted thing. I don't actually know any history here. I'm just saying, what I do know is that this was figured out in the early 1700s, and it was figured out by consideration of the fact that orbits are ellipses with the sun at one focus. Now, the people who had access to this information also had access to the information that the period squared was proportional to the semi-major axis cubed. A, don't love that. Maybe I'll call this G, the acceleration, call it G. It's actually much easier to infer this law from this fact than this fact. And in the contemporary way of doing things, we would always infer it from this fact, because we're all scaling dimensional analysis approximation type people here, so we would have done it that way. But that kind of arguing was not used back in the 1700s. I asked some historians, there's no evidence for dimensional analysis in the 1700s. So they did it the hard way, and the nice thing about doing it the hard way is there are many possible force laws that are consistent with this observation, but there are not many that are consistent with this. Because there was equal areas in equal times, and we knew that the planes of the orbits were not rotating. So there was a lot of evidence here that the laws of physics in the solar system were isotropic. Like the force law is isotropic, not just that it goes like 1/r², but that it's isotropic. There's no function of angle here.
What do you mean no evidence of dimensional analysis? Wasn't it Galilei 1700s comparing mice and elephants?
There were certainly people were interested in scaling laws, but it wasn't coming from the consideration of units. That's what I mean.
Yeah, well,
Anyway, it's an interesting thing to ask about. Good. Okay, now notice that what's important here is if you want to learn the force law, it's very useful to see the orbit. And if you can see the orbit, you learn the force law. And that turns out to be very true. Okay, now, let me make this is high-level point. My goal for the last 25 years has been to build a map of the dark matter in the Milky Way in phase space. So that would be like a 6-dimensional map of where the dark matter is. Why do I want to do that? Well, because that's the fundamental thing we might hope to observe in the Milky Way, and if we could get that, it would be very constraining on the possible theories of dark matter. Like, for instance, cold dark matter makes very strong predictions about what the dark matter looks like in 6-dimensional phase space in the Milky Way. What I want to do in the Milky Way is I want to see the orbits.
David, just
Yep.
you provoked the question.
Yes,
You
good.
always
That's
want
my
to-
intention.
Normally, it's a little hard to separate the impact of baryonic physics and the feedback that has gravitationally, forgetting possible
Yeah.
extra interactions. Does that is that less true if you have 60 phase space?
Good. That's a great question. Not obviously at small. It depends on where you're working in the galaxy. In the outer halo of the galaxy, I think it is true that it's way less affected. The phase space distribution of dark matter is way less affected by baryonic things. But it is true that near the center of the galaxy, where I'm actually going to be talking right now, for now, I'm just going to talk about baby projects because, by the way, I haven't succeeded in my goal. I don't have a 6-dimensional map.
Good, because you wouldn't be allowed to show it.
Exactly, I know. I'd have to draw it.
Yeah.
But anyway, but right, in reality, the CDM theory only predicts the details when you include the baryonic physics as well. So, good. I'm just going to punt that question. But I get your point. Yeah, I'm not saying that I have a clean test of CDM. I'm saying that fundamentally, if we measured the phase space distribution of dark matter, we'd actually know everything we could know locally.
Well, that's true, but I was wondering about the specific stress on the phase space. I often think, well, you know where I'm going.
Good, yeah. Phase space is way more informative than just position space, for instance.
It seems like it should be, since it's.
And the fundamental observation is the dark matter is cold. What does the C in cold dark matter mean? The C in cold dark matter means that the cold dark matter is essentially on a 3-dimensional subspace of 6 space. And that means even in our 6-dimensional galaxy, there should be the 3-dimensional the distribution of dark matter in the 6-dimensional volume occupied by the galaxy's halo should actually be a crumpled up 3 dimensional sheet.
Is that not true once you include the baryon?
It's,
That's what
it
I
is,
was trying to ask.
that's a great question. It is slightly violated by the baryonic physics because the baryonic physics is not always Hamiltonian in the right
Exactly.
ways.
And so it gets out of that paradigm, and then the gravitational interactive, which would be.
Is
okay.
perfectly conservative,
Okay.
yes. So that's why these predictions are more severe in the exterior part of the Milky Way than in the interior. So if you get out to the halo, at the halo, one thing, well, I'm going to remind you of properties of the Milky Way in a minute, but just to presage that, if you get up to the outer halo, the orbital time is of order of the Hubble time, so things do not phase mix. Structures that fall in stay coherent at the outside. And that becomes less true as you go in. Good. But my real goal, I mean, I have a kind of Mike Blanton attitude here, which is that it looks like we might be able to measure this, so we should.
Okay, I'll accept that.
Okay, great. So now, my kind of philosophy is if you can actually see an orbit or a set of orbits, so if you can see a set of orbits, you can infer the acceleration law as a function of position, and then you can infer where is the dark matter and everything else. That's my point of view. That's the point of view I'm taking. Good. And of course, there's stars and gas also contributing to this gravitationally. But I'm assuming we know so much about that. By the time I complete this project, we'll know so much about the stars and gas we can account for.
But here you mean orbits of tracers.
I would take, yeah, oh, yes, good. I mean like test particle orbits.
Okay.
I could deal with non-test particle orbits too, but the problem is way harder. So let's think of this as test particle orbits.
Okay, well, yeah, test particle or not, things that you can see, not dark matter.
Well, if we could see the dark matter orbiting, that would be cool too.
Yeah, no, I agree.
But you know, there's a, okay, good.
I have a question.
Yeah, hit me.
Don't we already know the Force law of dark matter? Like gravitationally, it behaves the same as ordinary matter.
But we don't know the distribution of where the dark matter is in space. So let me be a little more specific. I mean like the density of dark matter in phase space. Of course, actually, it's only the dark matter density in space that matters for any instantaneous snapshot, but when we solve this problem, we're going to get time dependencies and stuff. Okay, good. Okay, good. Now, I've been obsessed with seeing orbits in the Milky Way, and that's why you've heard me talk a lot about streams. There's stellar streams in the Milky Way. Sarah Pearson here works on that. That has been a really valuable direction. I love it. I still work in that direction. But the problem with streams is they only work in certain parts of the galaxy where you happen to have some kind of disrupted object. And if you don't know what I mean by stream here, too bad. There will be other brown bags in which you learn about stellar streams.
Very soon.
Good. Great. And then another, do I have anything else? Oh yeah, there's a tiny sense in which when you see spiral structure, you can sometimes infer some things about the orbits. I'm not going to talk about this either. This is a blunt tool, but sometimes, you know, the Milky Way disk appears to have spiral arms in it. If you could map them very accurately, you would learn something about the orbital structure of the disk. So this is an interesting direction. But the direction I'm going to talk about is called torus imaging. And it's a brand new method, and it was invented by myself and Adrian Price Whalen and Hans Walter Rix. And the fundamental paper about it is 12, 3 zeros, 3 zeros, and a 1, 5. 2012.00015. That means it's from December of 2020. Good. Okay, now, so this is the story I want to get to. I don't know if I'll make it. I'm going to try. I'm going to go slightly out of order here because I realized I kept mentioning things about the Milky Way there, so I'm going to tell you about the Milky Way for a second. The Milky Way is, if you saw it edge on, actually it doesn't look like this at all. This is the diagram everyone draws. It doesn't look like this at all, but I'm going to still draw this diagram. You are here in some coordinate system, and you are moving 229 well, you're actually not moving this speed, but the circular velocity, the circ, is 229 kilometers per second. And the best measurement of that was made by Christina Eilers and me this year, or last year, is the current best estimate of this, and that was based on the Gaia data. This is do a plus plus, there's a lot of authors on that paper. And you are very, very close to 8.2 kiloparsecs from the center of the galaxy. And that we know from a collaboration in Europe called Gravity. Not the force, but the collaboration. The Gravity collaboration built a very, very precise instrument that observes the galactic center so precisely that we know this number most precisely from that now. Good, and if you think about the halo of the Milky Way extends out to, I don't know, something like 200 kiloparsecs. There's halo out here, the dark matter halo. And the stellar streams that we know are kind of out here at like 40 kiloparsecs. There's some stellar streams that are useful. There's the Magellanic Clouds are also at around 50 kiloparsecs. Picture of the galaxy. Important thing, if you type into Google 2 pi times 8.2 kiloparsecs divided by 229 kilometers per second, it tells you that that math is 200 million years. So the orbital time for us around the galaxy, T orb for us, is 2 times 10 to the 8 years. That means you cannot see any stars orbit in the Milky Way. You will never see a star orbit. There's a bunch of stars we can measure accelerations for. They're all stars that are in binaries. So not only can we not even, and they're binary, and the acceleration is set by the binary motion. Not only can you not measure orbits, you can't even measure accelerations.
Yeah.
Yes, there are some proposals that might get low fidelity accelerations in the future, but you'll never see an orbit, at least by waiting and watching, the way that Tycho Brahe saw the orbits in that case. By the way, Tycho Brahe deserves a lot of credit for this one, because Brahe was the person who first really realized that taking precise measurements of the planets would be a good idea. Brahe realized you should measure what you can because it's going to be useful physically. So I think that Mike is directly in the tradition of Tycho Brahe.
Now you've gone too far.
Can I
Yeah, hit me.
so Sukanya, she has all this about accelerations of stars. What does she do then?
So the people who have claimed, there is actually an acceleration of the sun claimed by Gaia. And the way it works is they look at the proper motions of the stars and see that there's a net proper motion dipole on the sky, which is consistent with the time derivative of the relativistic beaming of the stellar positions. So in principle, if you have a billion sources with measured proper motions, you can just barely see the acceleration. They get like a few sigma acceleration for the sun. There's also, and Sukanya is working, there's a bunch of projects that do kind of collective things on large collections of stars to see an overall acceleration, but no way in orbit. I'm going to show you that we can get the orbits.
There's also a claim that a binary pulsar, with binary pulsar timing,
Yes.
you can measure the acceleration.
Pulsar timing should do it eventually. Unfortunately, most of the very good pulsars are in dense environments where there's local accelerations, but in principle, once you get enough of them, you will be able to see the overall acceleration in the galaxy. But you still won't see the full acceleration law or the orbit shapes. Okay, good. Let's talk about dynamics. So here's the things you're supposed to know about dynamics. If you don't know these things, don't feel bad, because first of all, the reason we moved dynamics from a required course to an elective in the undergraduate program is that I'm the only person in the department who does Hamiltonian dynamics, which seems like maybe that's changed since we did it, but when we did it, I was the only person doing Hamiltonian dynamics, so it was like, it's a pretty obscure thing to do. So don't feel bad if you don't remember these things, because they aren't actually used much outside of astronomy. So imagine I have a one-dimensional dynamical system where I only have one degree of freedom. I just have a position, I'm going to put it on this axis actually, a position which let's call Z. It's just a one-dimensional location. And then there's Hamiltonian dynamics of a particle in this one dimension. So the dumbest one is the simple harmonic oscillator, but you could go to any more complicated object as long as it has conservative Hamiltonian dynamics. So meaning no time dependence to the Hamiltonian, and it is actually a Hamiltonian system. Okay? Then you may recall that if you plot the velocity of this object on this axis, that no matter what your initial conditions, like if you start here, you will go on a closed curve in this diagram. And it'll be relevant to what I say in a moment, that this diagram is foliated with closed curves. What do I mean? I mean that if I go to any point in here, there's a closed curve that it's sitting on, and if I move it a small amount, I move to a nearby closed curve. But every point is on a closed curve, and all the closed curves, and if you wrote down all the closed curves, you fill space. With me? That is fundamental one-dimensional dynamics, okay? Next comment, you can rewrite this system in a new coordinate system, which you might call the square root of j cos theta and the square root of j sine theta, in which that orbit literally will become exactly a circle. And you will move around that circle exactly uniformly. And that is when j is the action, and theta is the angle, the corresponding angle corresponding to that action. Ring a bell? And there's a theorem, there's Hamilton-Jacobi theorem, which is about this. Good. Now, if you go up to, oh, by the way, an amusing thing is that J is the area of the orbit. Actually, it's 1 over 2 pi times the area of the orbit. Why is it 1 over 2 pi? Because when I take my angle through 2 pi, actually, am I right about that? Is it 1 over 2 pi? Anyway, there's maybe some factor in there before the angle of the area of the orbit, but basically the action is the area of the orbit. And so meaning, and remember canonical transformations, this is a canonical transformation. You may recall canonical transformations preserve area in this diagram. So the area inside that circle is the same as the area inside that circle. Good? Okay, great. Now, oh yeah, one more thing is that imagine I have a little particle here. You see, when it has high velocity, high positive velocity, it's moving upwards, and then it gets to a large z value, and then it falls down back to 0 velocity, and then it goes into negative velocities, right? So this is an object. If z is the vertical direction, this is an object that's doing this, which is like what stars do. Like this, a star does this around the galactic plane, which will come back to that in a second. Okay, good. And then if you do an integral, there's a nice integral you can do here. If you do the integral of v 1 over v dz, this is the period of the orbit. So if you show me an orbit here, I can immediately tell you its period. Good. That sounds trivial. That will not be trivial. At the moment, that will be very non-trivial fact. And by the way, this j being the action of, that means j is basically v dz. So the integral of 1 over v dz gives you the period of the orbit, and the integral of v dz gives you the action of the orbit. Good. Okay. So if you show me an orbit, I can tell you the period. So then there's one more equation which I want to write on the board, and people who've known me for a long time know that this is my favorite equation in all of physics. My favorite equation in all of physics is omega squared is g rho. Why is this my favorite equation? Well, first of all, this is the equation of cosmology. If this is h squared is g rho, remember that's cosmology. If you're a cosmologist, h squared is g rho. Great. Now imagine you're an exoplanet person, or you're a solar system scientist. Oh, what is this? Period squared goes like a cubed. Let's invert it. Frequency squared goes like 1 over A cubed, which is the mean density of the sun inside the stars or inside the planet's orbit. Or if you work on exoplanets, it's why when you discover an exoplanet, the main thing you measure about it is the density. When you discover a transiting planet, you measure the density of the star it's orbiting, not the mass. Okay, good. Great. So that means that if you tell me that if you show me this orbit, I can tell you things about the density inside that orbit. Because I can just read off the period, invert the period, square it, and that gives me the density inside that. Notice that's going to be a tool now that we have to measure the density everywhere in the Milky Way. Or the force law, as you like. Okay, good. Now, when I go to 3D, and actually it's better to go to 2D first before you go to 3D, because each D really sucks. Because even at 2D, things get very hard to understand. 3D, it's horrendous, but in 3D, the idea is that phase space is now 6-dimensional. There's 3 positions and 3 velocities, and it is foliated with closed 3 tori. What's a 3 torus? A 3 torus is like a donut, a classic donut that you can buy is a 2 torus because it's about the surface. It's 2-dimensional, meaning you can go through 2 pi around it this way or you can go through 2 pi around it that way. A 3 torus is that thing, but with a 3-dimensional surface. Enjoy. It's got a 3-dimensional surface and a 6-dimensional interior, right? And phase space is foliated with these 3 tori. Okay, great. Everyone with me? Now, if we wanted to, these are the orbits in some sense. If we could find those tori, in the same sense that if I could see, if you could show me all the orbits here, you know, whatever they look like, all the orbits there, if you could show me these orbits here, I could tell you where the mass is everywhere. Similarly, if you can show me these 3 tori, I can tell you where the mass
Sorry,
is.
David, I don't understand, because in
Yep.
6D you will become chaotic, so this foliation becomes meaningless.
Good. It's not meaningless, but you're right. This is, technically, this is only true. I was thinking to myself as I was writing this, I was thinking, I should say something about chaos, and then I was like, no, but Andre will ask. So, right, technically this is only true for what's called regular potentials, and there's none. Or integrable, sorry, the usual word is now integrable. For integrable systems, and there are no integrable systems, they don't exist. So everything I'm saying is a fantasy. However, our current models for the Milky Way that are realistic suggest that large fractions of the phase space are integrable, which means that the chaotic regions are confined. But it is true that out in the outer halo, this won't be true. But actually, the stuff that we do to orbit, the image of the orbits, doesn't depend strictly on this foliation being true. We rely on a different thing, which we'll see in a moment. But if you could show me the orbits, so the fact is, even when it isn't true that this foliation is the case, if you can show me the orbits, I can determine the density everywhere. So it is very valuable, even in the chaotic case. But you're right. Technically, this is only true in a subset of measure 0 of 3-dimensional potentials. Okay, good.
Can I ask you something?
Yeah, hit me.
Like, this is complicated for me kind of to embrace, because imagine you're an observer and you're orbiting something. Imagine Kepler. You don't care if the size is a point or a sphere. It's the Gauss law, right? I mean, the electric field or gravitational field of is, you cannot really tell the source by a field completely.
Good. Good. In this case, if you only knew this orbit and the orbits outside, there's a lot you wouldn't know. So we're only going to be able to learn the detailed distribution of the dark matter in places where we can see at least orbit segments. Turns out I only need orbit segments. I don't need full orbits. I just need orbit segments. But basically, if you see some orbit segments here, you can tell things about the density inside and the density here. So you learn some integral constraint and then some local constraints if you have a finite volume that you see. And that's, of course, the situation we'll really be in. Oh yeah, that was another thing that was worth writing. I've been talking a lot about Gaia recently. The Gaia mission is only really precisely measuring some kind of hourglass shape like this, and then imprecisely measuring, something much larger. But we are not seeing, for instance, the other side of the galaxy right now with any mission. Actually, SCSS-5 just barely touches the other side of the galaxy, and we can see the center of the galaxy. Actually, Eilers in that paper sees the center of the galaxy. Okay, good. Oh, I have notes. Don't follow me, I have just in my notes. Blah, 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 blah. Oh, yeah, okay, good.
Sorry,
Yeah.
I just have a question. So what will be your observables? So just velocities and positions? Is it
I'm just about to talk about that.
Okay.
So I want to talk a little bit about stellar abundances. Oh yeah, there it is, stellar abundances. So if you look at stars, okay, here's Hogg's cartoon of a star. There's a nuclear furnace in the center that's creating new elements, and then there's an envelope of the star that has some radiative zones and some convective zones. It's all very complicated. It depends on the kind of star and whatever. And then there's an outer layer, which you might call the photosphere. And this is what you see when you see a star. When you look at the sun, you're looking at the photosphere. It's 5,700 Kelvin. Don't look at the sun without eye protection. And then if you take a spectrum of the sun, what you find is you get a spectrum with absorption lines in it. Here's wavelength, this is some intensity, this is a spectrum. And these lines correspond to particular elements. And there was a huge discovery in the 1800s, late 1800s, by Bunsen of the Bunsen burner and Kirchhoff, of Kirchhoff's laws, that these lines are in exactly the locations of laboratory lines, and they contain, they're magnesium lines and nickel lines and iron lines, and that's how they figured out that the sun is made of the same elements as you have in the lab, except for one element they couldn't identify, and so they called it helium, the element that only exists in the sun, and then it was discovered about 10 years later. So when we measure a star, we're getting to the observables now, you can measure a few things. One is you can measure a redshift, so you can measure a velocity for the star. The other thing you can measure the star very easily is you can measure its position on the sky, which you can think of as theta and phi in a spherical coordinate system, and this combines to be a full three-dimensional position. No, it does not. This is two parts of your position. We're working very hard on distances to stars, and Gaia famously does parallaxes, but there's lots of other ways to estimate distances. That's a lot of what we work on. These three give you a three-dimensional position. This gives you one of your dimensions of velocity, and then there's proper motions, what are called proper motions by astronomers, which is angular rates of change of these two angles. So this gives you the transverse velocity with the distance, and this gives you the radial velocity. And so in the ideal case, we have six-dimensional phase-space positions for a very large number of stars now. And it depends on precision, how many stars. If your precision requirements are weak, tens of millions. If your precision requirements are high, hundreds of thousands of stars with six-dimensional positions. But because we have these lines, we can also measure the element abundances, which we usually ratio to either hydrogen or to iron. Although maybe I should go modern. In contemporary usage, we normalize to magnesium. So you'd have Fe to magnesium, nickel to magnesium, and you won't get the joke I was just making, but there's a small group of nucleosynthesis people, and Emily's one of them, that wants us to start thinking in terms of ratios to magnesium rather than ratios to iron for very good reasons. But anyway, by looking at these lines, you learn ratios of the abundances of elements, and then in common astronomical practice, you put it in a square bracket, and that says relative to that same ratio in the sun, n log base 10. It doesn't matter. It actually doesn't matter what we mean by these numbers for what I'm going to say next. It's just that we have numbers which are related to the abundances, the surface abundances of the star. Good. And the biggest project doing this right now, I think, is SDSS-5, although there's other projects hot on its tail, and SDSS-5 has collaborators here, including Mike and me, and one of the biggest projects prior was SDSS-4, which Mike Blanton directed and fundraised. And these projects are big projects that involve a lot of people, many institutions, and big hardware, and very, very beautiful software. These are very big, important projects, and I'm proud to be a part of them. Okay, good. One last fact about stellar abundances is that the surface abundances are constant in time. This might seem weird to you because you know that stars make elements. They are literally the things that make the elements, and people famously say, you're made of star stuff, which is true by mass. You're mainly star stuff. Your hydrogen, though, is Big Bang stuff, which is, I think is cool. But anyway, you're made of star stuff. It's cool because what happens is the stars make all sorts of elements in here, heavy elements in here, but they only actually give those elements back to the universe when the star blows off a wind or goes supernova. In the late stages of stellar evolution, the sun will turn into a big giant and it will slough off some winds. And then, depending on details, some stars will explode as a supernova, some will collapse into a neutron star, or a white dwarf, various things happen. But these elements that the star makes only come out at the end of life. When we're observing them in their normal parts of their lives, these abundances are constants. They don't change with time. That there are exceptions, if there's any expert, well, there is an expert in the room, there are exceptions, and you're just being polite, because there are some elements that through magic get dredged up from the interior of the star, but it's quite hard to do. And it's only in certain stellar types. Okay, good. These are our observables. Notice we don't have any orbits here. We just have positions and velocities and a whole bunch of abundances. Let's say we have something like 10 of these abundances. Maybe we have 15. Actually, Apogee measures 15 abundance ratios, but not all of them are all that good. Other surveys measure 30 or something, but don't have as many stars, whatever. Think of it as of order 10 of these elements that you measure. We can't see, there are a few stars where you can see a large fraction of the periodic table, but those are very, very bespoke observations of individual stars. Has the whole periodic table been seen in the sun, do you know? I don't think it has, right? It's only about 40 elements, I think, in the sun. So and the sun's a pretty good target because we get a lot of photons from the sun. Okay, good. Okay, we have all the pieces. Let's put it together. Okay, good. I've told you all these things. God, I hope so. Yes, I've told you all these things. Okay, here we go. Okay, so imagine you have a dynamical system. I have a dynamical system. Let's consider this 1D system, because actually I do kind of have a 1D system. It turns out if I look very, very nearby in the Milky Way disk, I can look at just the vertical motions of the stars, and they don't perfectly separate from the radial motions, but they separate enough that you can actually think about the vertical oscillations of stars around the disk, the little oscillations I drew there, as being a one-dimensional dynamical system. So let's think in one dimension for a bit just to keep things simple, partly because I cannot visualize a 3 torus, let alone a 3 torus embedded in 6D. So let's just think about it like a 1D dynamical system, but it could be any dynamical system. And imagine this dynamical system has invariance of motion, meaning there are dynamical properties of the system that don't change with time. And in a one-dimensional system that's conservative, that could be the energy of the orbit. That's an invariant with time, the total mechanical energy, potential plus it. Or it could be this action we computed, which by the way is very related. Or it could be anything. It could be the period of the orbit. Like anything that is the same in the orbit as it goes, these are dynamical invariants. So let's call the invariants of the motion J, and let's say there's a set of them, although in one dimension there's only one invariant of, you only need one invariant in one dimension, but if we were up to 3 dimensions, we would need at least 3 invariants here. Okay, now imagine that you have a steady state. Oh, one thing I love, the famous book on all of this is Binney and Tremaine, which is the dynamics. It's called Galactic Dynamics. It's a very heavy book. I mean, literally, I can't lift it. And it's a very theoretical treatment. I kind of object to it because it's very theoretical, although I think it's really filled with a lot of insight. But that book opens on the first page. They say, well, the orbital time of the sun around the galaxy is like a 40th of a Hubble time or something. So therefore, we can expect the Milky Way to be a steady state dynamical system. And the opening line of my book will be, the orbital time of the sun around the center of the galaxy is about a 40th of the Hubble time, so we can't possibly imagine that it would be a well-mixed dynamical system. But anyway, the theory, it does turn out that the parts of the galaxy near us look very mixed. And for instance, when we look at this vertical, when we look at the distribution of stars in the vertical height and the vertical velocity, it looks very smooth, and there's a very subtle spiral feature in there, which Surer has written a paper about. But basically, that Milky Way looks surprisingly well mixed, given how young it is. But if you were in steady state, then the distribution function, so a dynamical concept I didn't mention up there, is there's the concept of the dimension of the distribution function. This is what I want to learn about the dark matter, but the distribution function is the number of, it's the density. You can think of it as the density or the number density or the number of objects, or you can think of it whatever, per unit volume of space, per unit volume of velocity in 6-dimensional space. So this is like a density, a 6-dimensional density. Remember, we have positions and velocities, so there's a 6-dimensional density in play, and the distribution function has units of per volume per velocity. And if there are invariants of the motion and you're in steady state, then this function can be written as a different function of just your invariant, or your set of invariants. Because, and why is that? It's because in steady state, the density, your phase space density doesn't evolve in a Hamiltonian system. That's Liouville's theorem. And therefore, it can only depend on other things that don't evolve. Anything that doesn't evolve can only depend on other things that don't evolve. So this doesn't evolve with time. This density doesn't evolve in time in the right unit coordinate system, and that's the right coordinate system to show it. Make sense?
This is only true for time-independent potentials?
Yes, I'm incorporating that into steady state. Yeah, and actually over here, this idea that this is foliated with closed curves also depends on being time independent. Because you can imagine if you're time dependent, they become like spirals or something. So right now I'm doing time independent. I believe that everything I'm saying will generalize, it's just it won't have any beautiful math behind it. And it will become a computational problem. Actually, a lot of things in dynamics are like that. There's beautiful math in Binney and Tremaine. You refer to it just like this, refer to the beautiful math, and then you immediately go over to a computational model and never look back. And that is quite likely where we're going. Actually, there's an open problem that I'm so interested in, if anybody's mathematically inclined, which is to give me a description of all possible 3 torus foliations of a 6-dimensional space. If anyone can solve that problem, first of all, you'd be famous, and second of all, we'll use it. Okay, good. Where were we? Oh, right. Okay, good. It's about to happen. So here we go. So now, imagine, let's go back to just this simple case, which is very easy to visualize. But everything I'm going to say will generalize, but let's just think about this simple case. So now, imagine I take a little location in phase space, and this contains, say it contains on, like, the problem is there's a finite sampling issue, but let's say there's a, let's just talk about this density. So there's some, it's called Z in this case. There's some density F at this location in that little neighborhood there, you see? Now, if you imagine this thing orbiting in time, it will eventually get to, say, here, and that means this F here has to equal that F there, because phase space density is conserved in Hamiltonian systems. That's Liouville's theorem, and we know that we go along that closed orbit. But that means that if you made a plot for me of this F in this space, if you could make a plot of this F in this space, the level sets of this will be orbits.
But only if you use the right transformation, right, to make it completely circular. And how do you know if you did that?
It turns out you don't have to make that transformation because the canonical aspect of it saves you. If you make a canonical transformation of this to another coordinate system, as long as it's canonical, F will still be the same in those two locations, as long as it's canonical. So under any canonical, in any canonical coordinate system, this is true. But it's easiest to visualize in the circular case, but it's always true. Okay, good, great. So that means, what happens if I look at the Milky Way disk? Well, it turns out there's a lot more stars here, and there's a lot fewer stars here, so there's a smooth run of density. And if you just contour that density, you see the orbits. The only problem is, the Milky Way is a big, complicated object, and we don't actually look along all lines of sight equally, and so it's actually very hard to perform that experiment. But that is an experiment that a lot of people in particle physics are interested in these days. People are thinking about modeling steady state systems, and Oren does things like that. And people usually think about this phase-space density. But the problem with this phase-space density from my perspective is it's very hard to measure. And it's very hard to measure because we have all sorts of selection effects which make it easier to see stars in some parts of phase space and harder to see stars in other parts of phase space. For instance, there's a censoring along this axis here by dust in the galaxy disk, and there's all sorts of things that make observing this phase space density directly very challenging. But we'd love to do that. If you get the phase space density, we'll use it. And everything I say would work there. Okay, good. Now, so the weird thing about this thing, I just want to write it down. Level sets of F are orbits.
This is in 1D
Instead.
only, right?
It is also true if you really had an integrable system with a 3 torus that was well mixed. And by the way, it's quite hard to mix a full 3 torus. But if you really did, then it would be true of every point on the surface of the 3 torus would be at the same value of F. So these 3 tori not only foliate space, but they are the level sets of the distribution function.
But I can't invert anymore because I only have one F and I'm in 16.
That has something to do with, yes, you can't invert. And I don't fully understand that, but it has something to do with the fact that you have it's very constraining that they're closed and it's foliated. So it's some topological thing comes into play, but it's not invertible.
So David,
Yeah.
it seems like maybe I didn't hear well, you're forced to make a steady state, time independent assumption, but we know things have fallen in. And I wonder if it's actually
Good.
useful.
Yeah, well, the funny thing is I'm not forced to make that for the following reason. Imagine we weren't in steady state, and imagine we're not in I mean, it is true, well, I really have 2 answers to that. There's one, there's very far from steady state, like everything's on first infall. What I'm going to talk about won't help very much. There's another regime which is you're close to steady state, but there's a perturbation, a low order perturbation that is like winding up as a spiral or something in the system. That's the case that Surer has studied. And everything I'm doing here would generalize to that, because we can do everything I'm about to say. I haven't actually said what our plan is, but what the plan we have generalizes to that case as well. There's an intermediate case that I'm interested in that I think will also work, which is where it's not necessarily steady state, but you do know that you want to figure out that this patch is on the same orbit as this patch. You don't have to assume that the full torus is mixed, but you have to assume that some set of angles local to these observations are well mixed. So for instance, when we look at the solar neighborhood, if we're thinking about the orbital mixing this way, we don't actually get to see the whole torus around us. So we only have to assume that it's well mixed very locally to the sun, which is a much weaker assumption than the whole torus is well mixed. Because things mix locally, they stretch out locally along the orbits. And so I don't actually, for the realistic experiments we'll eventually do, we don't actually need the whole thing to be mixed. We just need there to be nothing too dramatic to have happened in the last orbital times. But you're right. There's definitely assumptions being made here. By the way, all modeling of the Milky Way density is based on an assumption of steady state. The only thing that isn't is the stellar streams. The stellar streams only depend on there being accelerations, but even the stellar streams are usually analyzed in that state. So though I am making bad assumptions, they're assumptions that everyone makes at present. Non-equilibrium dynamics is not a solved problem. And we have some approaches. That's what I'm working on, actually. One thing, I'm not going to tell you about this here, but everything I tell you about here, we have this first order perturbation theory departure from equilibrium model as well. Okay, good. Now I can tell this the final story. Okay, good. I have seconds to go. What am I working on? I don't want to erase my galaxy, I don't think so. Here, I can erase everything about abundances. Okay, I'm about to use what I'm erasing about abundances, but they're constant in time. The abundances are constant in time. The abundances are constant in time. Oh, we were just talking about invariance. There's an invariance which is that phase space density is conserved. There's an invariant that says that the f, the distribution function, is conserved along or invariant along the trajectory. The abundances are also invariant along the trajectory. So let's go back to my diagram, ZV, and I have a little patch here. Now imagine I look at the distribution of abundances I see in that patch. There are some mean abundances. There's some variances, some variances, some medians, whatever. I can take various statistics of the abundances of the stars in this patch. And as this patch moves, because all of the stars stay the same, the stars in the patch stay the same, and the abundances in the patch stay the same. Therefore, anything I can measure about the abundance distribution here has to equal anything I can measure about the abundance distribution here.
I should think about the length of time here is less than an orbital time.
Well, actually, we're just going to get a snapshot right now. So we're actually going to talk about two completely
Right,
separate patches.
but you were assuming that those are connected. How long ago were they connected? Or how long ago?
Well, of course, this one was over here
Yes.
when that one was there. But so I'm essentially assuming that the timescale on which the abundances change and stars are born and die and new things fall in and all that stuff are much longer than the orbital time.
Right. Okay.
I think that's the only real assumption.
Okay.
It seems like you also have a homogeneity assumption, like suppose you have young molecular cloud one place and something that's not a young molecular cloud the other place.
Then I think you wouldn't be able to say you were in steady state.
Well, I'm just saying that.
Yeah, but there are molecular clouds.
I see. Yes, there are. So this will not be a good thing to use on very young stars or on star-forming regions or on gas clouds. Things that evolve on short time scales we're not going to use. So in fact, what we're using, because they're the tracers that are best, are red giant branch stars, which live for about 1 billion years, and they don't change their abundance during those 1 billion years. So they live for multiple orbits, and they don't change their abundances. Yeah?
I think you might have just answered it, but what about radial migration and migration due to like resonances from the bar that actually move stars completely from where they're born?
That actually helps me,
Okay.
it turns out, because that helps with the mixing. But you're right that it's not that is evidence. The fact of what she's referring to, by the way, is that stars don't orbit at their same radii forever. They actually change radii because of resonant interactions with the bar and things like that. And so, for instance, we think the sun formed further out and came in, I think.
I don't remember which way it goes.
I think it's out and came in, do you know? Anyway, it's one of those.
Seems like we should know the answer to
I
that.
I should know the answer to that, but I don't. The sun's pretty young, so it's probably out and came in, I don't know. And that just means that really the galaxy is not in steady state.
But wouldn't that mix up your interpretation of the abundances?
I'm not going to interpret the abundances, but what it means is that if radial migration is preferentially inserting at some phase of this orbit, then there will be a phase dependence to the abundances.
Yeah.
So I'm kind of assuming that the migration is not preferentially inserting at a large rate at one phase. Other than that, I don't care about it. Okay, so if I'm right that any moments, so let's call these things moments, I can take moments of the abundance distribution. Here, I can take moments of the abundance distribution. I can take moments everywhere. And when you do that in the local galaxy, if you just take vertical height above the disk, this is now we're in the disk plane of the galaxy. This is height above the disk. This is like velocity, vertical velocity. This is velocity in the z direction in the Milky Way. And you plot what are the abundances of stars. They're beautiful. The plots are so beautiful. You get there's a cold population. What do I mean by cold? It's low kinetic energy. It always stays near the plane. That is high metallicity, and it gets lower metallicity as you go out. And so you see contours that look like this. Let me erase this. And in fact,
So you're doing this because you can't measure the density in this
because
space.
I can't measure the
Okay.
density very accurately anywhere.
In the ZV space or in the galaxy?
This is in the galaxy in ZVZ. So
Oh, okay.
Z direction is vertical here. And yeah, I didn't draw my coordinate system.
Oh, I understand why you're without with the vertical oscillation.
You're not going to like my coordinate system. The coordinate system has X going this way and Z going that way, and Y either left-handed or right-handed, depending on whether you're Bovie or Adrian. Two students from this department are battling on the world stage about whether this coordinate system is left-handed or right-handed.
One was an undergraduate and one was a graduate, so we should get those programs to be consistent.
Good, so I'm literally talking about, and I'm talking in our neighborhood where we have all this data, in the hourglass.
Are these levels dependent on which characteristic you use?
That's what's so cool. So we can plot different elements here, and actually some of them have an opposite sign. Like some ratios, the ratio, like if you look at the what's in the lingo called the alpha abundance actually goes up as you go out. The metallicity, what's typically called metallicity, goes down as you go out, but the level sets are the same shape when we look at the different
Really?
elements. Yes. And this whole project, actually, I should say, this project is by Adrian Price-Whalen, Hans-Holger Rix, and me, but it was inspired by a plot that was shown to us by Melissa Ness, who is giving the Astro Seminar tomorrow. She showed me a set of plots that had different abundances in this space, and they all had the same level sets. And I was like, oh my God, you can just see the orbits. Because we just see the orbits, and it's really detailed. It's not that they all look circular. It becomes diamond shaped as you approach a separatrix here with the orbits that are unbound into the halo. So you can actually measure not just the mass of the disk locally, you can measure the ratio of the disk mass to the halo density locally. And so just by looking at these plots, we can see the orbits vertically in the disk.
These are disk stars, basically.
They are disk
They're
stars,
disk
the red
stars,
giant
the red
branches
giants.
in the disk.
What's the relationship between this and the age velocity dispersion relation?
It's very related.
Is it the same thing though?
It probably
or-
is. If we had stellar ages, actually, the TESS mission, combined with various things, has done astroseismology to determine ages of red giants. And when we plot the age distribution, it looks like this as well.
Yeah, I mean, yes.
And
I guess I'm just
these are the
wondering-
younger ones, and these are the older ones.
Like, is that what's going on?
I don't care what's going on. I want to see the orbits.
Sure.
But
okay.
if somebody cares what's going on, there's two possible explanations. One explanation is that the older stars were heated by interactions in the disk. And the other explanation is that the disks that formed at earlier times were hotter and the later formation processes were colder. And both of those explanations are competitive right now. But yes, this is what actually sets this up is actually interesting galaxy astrophysics if you care about astrophysics. But if you care about dark matter, we can actually map now the dark matter locally, the vertical distribution of dark matter locally, just by looking at the abundances of stars. And the current projects that are going underway is one project with Adrian Price Whalen and Danny Horta-Darrington, who's at CCA. We're looking at the midplane. You also measure the midplane, by the way, because this doesn't have to center here. It could center down here. And we can see that the midplane of the Milky Way has a more warp in it at the outskirts. We can also measure the scale height and the density of the disk, and we can see that the density of the disk falls exponentially from the center of the galaxy by doing this operation at different radii. So with Danny Horta-Darrington, we're doing this project of like using these models to measure the density of the disk. And then the other project I should mention is with Alexander Novara. We are doing a model-free thing where we're just trying to measure the gradients of these moments locally and see if from the twist in the gradients of the moments locally, we can measure the acceleration of the sun towards the center of the galaxy. I'm done. End of story.
So briefly, questions, especially from non-usual question askers.
Yeah, I have a question. So I'm very confused about this relationship between abundances and orbits, in the sense that in your initial characterization of the relationship between invariants, the density function, and the orbits, at least in the standard way of doing things, it's crucial that the invariants depend on the canonical variables.
Yes, right.
That's what you wrote there. Whereas
yeah.
these are sort of independent labels that you are.
Exactly, yeah. So there's a paper that we're writing with Tremaine, Nej Frankel at CETA and Scott Tremaine and I are writing a paper where Scott rederives this result, where these are the abundance moments. So this can be derived just from a consideration of like collisionless Boltzmann equation. You just need conservation. Here it's conservation of stars, and in ours it's conservation of like iron nuclei. And then we're able to get it. And so the expression we get actually says it's yet another function of where this function is a function where this is an abundance moment, or a set of abundance moments, which are a function of position and velocity. So it is true that we have to be able to measure these abundance moments as a function of position and velocity. But once we do, if the system is close to steady state, the level sets of those have to be the orbits, basically. Another way to say it, which is more like how Novara is thinking about it, is that the gradients, because what astronomers always talk about gradients, what's the metallicity gradient? The gradients have to be perpendicular to the tori. And that's why we actually originally called this like chemical tangents or something. This project has had a bunch of different names because the orbits are tangent to the gradients of the moments.
Perpendicular.
Yes. Yes, sorry, perpendicular. Yeah, sorry, the opposite of tangent.
The opposite of tangent.
The opposite of tangent. Perpendicular.
Okay.
Were you going to ask something, Matt?
I'm
sorry.
I was wondering, like, what the largest source of error for, say, getting the dark matter out of this, given our 60 phase case.
Good. That's such a good question, and of course the answer is an entire other brown bag. But the short answer is I've erased it here. We are very bad on distances. The distances are by far the worst thing we measure. Even the best distances we have are worse than everything else there. And the second thing are like Glynis's concerns. There's no way that we're in a steady state. And so we are losing precision by making that assumption.
All right, let's thank David again for keeping and stop recording.
That's really
Thanks.